Let's take a look at this problem, taken from the Asian Pacific Mathematical Olympiad 2019. It says, find all the functions f that maps the sets of natural numbers to itself, such that for all natural numbers a and b, f of a plus b divides a squared plus f of a times f of b. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. I'm going to share with you two solutions to this problem, coming from very different ideas that both came to my mind when I noticed the fact that this function is mapping the set of natural numbers to itself. The first one is that because we are dealing with natural numbers and at the same time is a divisibility relation, I'm going to consider apart from some of the very common values such as 1, I'm also going to put primes into A or B, because if I can somehow rewrite the dividend in terms of a prime number, then I can minimize the number of possibilities of the divisor. So here's the first method. I'm going to first put A and B to be both 1. Then this expression will become f of a, sorry, it's a typo, f of 1 plus 1 will divide 1 plus f of 1 whole squared. Now, to derive further results, I'm going to rewrite the dividend by adding or subtracting some very well-known multiples of the divisor. And in this case, I'm going to subtract f of 1 whole squared minus 1. This expression is clearly a multiple of f of 1 plus 1 because of the difference of square identity. So we know that f of 1 plus 1 divides 2. And now because the dividend is 2, so the divisor can only be 1 or 2. So f of 1 plus 1 can only be 1 or 2, which means f of 1 is 0 or 1. And of course, we reject the 0, so we know that f of 1 is 1. So that's the first result we have achieved. Now, the next thing that I'm going to do is to only put one of the a and b to be 1, so and see what will happen. So now we know that f of 1 is 1, and so if we only put a equals 1, then we will have 1 plus b, because f of a is then 1, will divide 1 plus 1 times f of b, so plus f of b. Then, so at least we can say that b is less than or equal to f of b for all b. Next, when b equals 1, we'll have f of a plus 1 divides a squared plus f of a times f of 1, which is 1. And I'm going to simplify the dividend, which is a squared minus 1. Now from this, again, I can say that f of a should be less than or equal to a squared minus 2, because the divisor should always be less than or equal to the dividend. So combining, I can say that f of n, for all natural numbers n, f of n must be between n and n squared minus 2. So that's the second result. Now, after making full use of the 1, I'm going to try to put in some primes. Now, for any prime p, I'm going to put a equals p and b equals f of p instead. So the divisor would become a much simpler expression. But the dividend will become p squared plus f of p times f of p. Now, 2 times f of p divides p squared plus f of p times f of p. most people would believe that the larger the divisor, the more complicated the divisor is, the more we can simplify, the more we can reduce at the dividend. But in some occasions, on the other hand, the smaller, the simpler the divisor is, the more flexible the expressions we can bring in to simplify the dividend. So in this case, I'm going to say, in particular, I'm going to remove the 2. F of p divides p squared plus f of p times f of p. And of course, at this stage, I can remove the second term, and that will make f of p divides p squared only. Now, this is a much more useful result because p squared has very few divisors, which are 1p and p squared only. So f of p can only be 1p or p squared. But from the bound we have achieved just now, we know that f of p can only be p. So that's the third result. Now, having known this, I'm going to rewrite just a equals p when a equals p. Then p plus b divides p squared plus p times f of b. And now I'm going to say that p squared plus p times f of b minus p plus b times p plus f of b over p plus b is still an integer. That's simply the quotient from the divisibility minus p plus f of b. So simplify, I can get minus bp minus b times f of b. And of course, I can remove the minus signs. We can scale it, and it's still an integer. After, I'm going to further subtract. Minus b times p plus b, and it's still an integer. And finally, we have removed all the prime terms at the numerator, and the rest are just in terms of b. Now, however, p is arbitrarily large, and if we fix b, the numerator will be arbitrarily large while the numerator is actually fixed. So because p is arbitrarily large, therefore, the only possibility for that fraction to be an integer is that the numerator is 0. So that means f of b equals b for all natural numbers b. After fixing any natural number b, we can achieve this. So this again holds for all natural numbers. So therefore, f of n equals n for all natural numbers n, and we check. If f of n equals n, then a plus f of b equals a plus b, and a squared plus f of a times f of b equals a squared plus ab equals a times a plus b, and it clearly is divisible by a plus f of b. So we give a tick, and we know that this is the only solution. The second method that came to my mind is that because we are dealing with natural numbers, so in fact, I can actually translate this part into another phrase, which is for all positive integers. Well, this sounds very unnecessary, but whenever I see these kind of phrases, I would try to use induction. It's just like whenever you see a graph theory problem, you will try to perform induction on the number of vertices because of the graph, because you always know that the number of vertices in the graph is a positive integer. So I'm going to perform induction on this. I'm going to continue from after achieving the result that f of 1 is 1. We know that f of 1 is 1. So now I'm going to assume that f of k equals k for some positive integer k. And in fact, I should add a few more lines before that. Claim that f of n equals n for all positive integers n, and proceed by performing induction. So after assuming that f of k is equals to k, then the final thing that I have to do is to show that f of k plus 1 is indeed k plus 1. So the final statement that we're going to face only involves two numbers, k and k plus 1. So the only thing that I can possibly do is to put a and b to be k and k plus 1 respectively, or the other way around. So the first thing, when a equals k, b equals k plus 1, then I will have f of k plus k plus 1 divides k squared plus f of k times f of k plus 1. Then it will become 2k plus 1 divides k squared plus k times f of k plus 1. So I can scale up the dividend a bit to make the simplification easier, because I have a 2 at the device. I have a 2k term at the divisor. So 2k plus 1 divides this new dividend minus k times 2k plus 1, and I will have minus k. So let's leave that there. And on the other hand, when a equals k plus 1 and b equals k, I can say that f of k plus 1 plus k divides k plus 1 whole squared plus k times f of k plus 1. So f of k plus 1 plus k divides k squared plus 2k plus 1 plus k times f of k plus 1. And we can quickly remove the k times the divisor. And so divides 2k plus 1. I can also try to rewrite the first case, which is that when I replace a to be k and b to be k plus 1, I can further simplify, kind of, and make it minus f of k plus 1 times 2k plus 1. Well, clearly a multiple, and I will have 2k plus 1 divides minus k minus f of k plus 1. And actually, I would achieve this. So now, at a close look, you will see that these two are the same, and these two are the same. So they actually divide each other, and so I can conclude that f of k plus 1 plus k is equal to 2k plus 1. So f of k plus 1 is obviously k plus 1. And there we go. We've finished the induction step. Therefore, by induction, this is true. And of course, we don't have to check again. We have checked that in our first solution already. So, yay, we are done. I hope you enjoyed the video. Feel free to suggest any alternatives in the comments. If you like my videos, make sure to subscribe to my channel right now. Thank you for your support. See you next time.